In this topic packet, we're going to just look at the basics of integration, starting with the three main rules that are usually taught as you learn integration techniques. That's going to be your sum and difference rule, your power rule, and your constant rule. So this will be a quick one just to clarify those and work through a few examples together. Listing out here, you can just see the goals of this topics packet in the table of contents. So hopefully by the end of this, you have a better feeling for the sum and difference rule, what it's saying, how to manipulate algebraically before integrating using some of these basic rules, and then start working on that power rule, which is a big rule that you'll be using from here on out in your integral calculus course. So getting a start here, the main rules that we're going to look at today are enumerated here before us. So the sum and difference rule, just to highlight what it's saying. I know you can read what the rule states mathematically, but to highlight what it's saying, it's just saying if you're integrating a series of terms that are being added or subtracted, you may treat them separately and integrate each term separately. So you could either split it apart into two different integrals, or you can just go down the line and integrate each term individually if they're separated by a plus or minus sign. Be careful, if terms are being multiplied or divided, you may not treat them separately. You need other rules to integrate products of functions or quotients of functions, and those are more complicated rules that are going to come in your class as you continue learning. The power rule teaches you how to integrate something of the form x to the n. So x, your variable, raised to an exponent, and it's okay if that exponent is a fraction, a whole number, a negative number, anything except the number -1, which we'll get into in one of our examples why the power rule doesn't work for x to the -1. And then we'll take a look at that constant multiplier rule. That constant multiplier rule talks about if you have a constant multiplying a function, you can just take the constant out in front. It comes along for the ride when you integrate, so you can take it out in front of your integration, do your integration, and then just tack that constant along in your final answer. So let's get started with example 1.1. On top of teaching you these rules, since we're just getting started with integration, I'm also going to try to teach you some of the terminology used and notation used with integration. So example 1.1 asks us to evaluate the following indefinite integral. What makes this integral sign an indefinite integral is that we do not have any limits of integration written. Therefore, we are just looking for a general antiderivative formula of the function that is written in the integrand. So this function box right here would be referred to as the integrand of this integral. Now, notationally, what does this mean? If you think back to when you took differential calculus, so just trying to connect the dots here. When you took differential calc, some of the notation you might have seen used is the following. You have a function f of x, and then you find its derivative. And in this context, we are now starting with the integrand being the derivative function. And your job is to go back and figure out what could the original function have been. Now, in integral calculus, in many classes, I don't know your class specifically, but in many classes, we change the notation a little bit. We just change the perspective. So we now start referring to the derivative as little f of x. So we would call that integrand little f of x. And we would call its generalized antiderivative big F of x. So this is what we're looking for. Again, it's analogous to differential calculus. We just kind of changed the notation up. So one thing you want to remember is the relationship between big F and little f in your class is just the relationship of a derivative. Little f is the derivative of big F. Similarly, f prime is the derivative of just the little f function. So that's just a kind of note on some notation you're going to see. Let's tackle this example now. So I'm going to bring this down. Now you'll see the way the problem is originally written has parentheses around the entire integrand. That is appropriate to do, but it's not commonly done. I actually think it's unfortunate. I wish we would write those parentheses around the entire integrand all the time. We just don't. They are implied. So if you see the problem written without a large set of parentheses, you have to just remember there is an implied set of parentheses there that we just don't write. Now, the sum and difference rule, I'm just going to move down to get us more room. The sum and difference rule tells us that we can split across plus and minus signs. So what this means is I can actually split this into 1, 2, 3 different integrals if we split across the plus and minus sign. Notationally, this would look like the following. Right? So what this is saying here is instead of integrating one long string, because there's pluses and minuses, the sum and difference rule says I can split each integral term and integrate each term separately. Notice that I was mindful to take my signs, the negative sign when appropriately and the positive sign when appropriately. Now, just to point out, most people do not actually take the time to write out the split unless the integral is extremely complicated and they need to split it up to visualize what's going on. So this splitting process is something you'll start doing probably more later on in the class when things get a little more intense integration-wise. Most people just continue from the form where everything's together, and they mentally know that they can integrate each term separately across a plus or minus sign. So that's the way we're going to proceed, because it's most likely the way you'll see in class, is we'll keep the integral together, but we'll just integrate each piece separately. Now, there also is some wisdom here before we get started. The wisdom is seeing, oh, there's a square root of x. Remember, if I think about what the indice and the exponent of those are, I just squeeze those in very light. This is going to help me rewrite that square root of x as a power. I want to rewrite everything as a power, not leave it in a square root form. So rewriting this problem gives me the following. Remember, when you rewrite from the root form to an exponent form, the exponent on x is the top number of the fraction, and the root indice is the bottom number of the fraction when you go to an exponent. So now I've got my problem set up and I am ready to integrate. So this term equals here. Focusing on one term at a time. So I'm going to look at 2x to the third. This constant multiplier rule tells me the 2 comes along for the ride because it's multiplying the x to the third. And now I'm going to apply the power rule on the x to the third term. So the power rule tells me you add 1 to the exponent and you divide by the new exponent. Of course, we know 3 plus 1 is 4. You could have just written 4 there. You don't have to write that plus 1. You could simplify that as you go, but for the sake of learning together, I'm just going to show it kind of in all the steps and we'll simplify later. So this is an antiderivative of the first term. Now let's move along to the next term. Remember, there's like a -1 multiplier in front of that x to the 1/2. So that -1 comes with us. We just don't tend to write the 1 in front. And then we apply the power rule to the x to the 1/2 term. The power rule says add 1 to the exponent and divide by the new exponent. I'm going to just shrink this down a little bit to get us more room before we get our final term in. Awesome. So we have now integrated the first two terms. Move along to the 4 term. Now keep in mind, just in case you're thinking of power rule, 4 is the same thing as 4x to the 0, right? There's no x's present. So we can apply the power rule actually on that x to the 0 term. So this would be written as 4x to the 0 plus 1 divided by the new exponent, 0 plus 1. And then remember, as you should have talked about in your class, there is a potential for a constant here, a plus c. Because you want to think, why does that plus c exist? Think backwards. Think if you took the derivative of this function here, the derivative of the plus c would be 0. So it doesn't matter what that constant is or was, we just need to account for the fact that there could have been a constant there. So cleaning this up, this becomes 2x to the 4th over 4 minus x to the 3 halves over 3 halves plus 4x plus c. And I'm just going to take this into one more cleanup step just to make this a little nicer, reducing our fractions. But I do want to point out this is what we have written here. This is a valid final answer. So you could box this as a valid final answer, but let's just clean it up one more time, reduce our fractions, etc. This could clean up to 1/2 x to the 4th minus 2/3 x to the 3 halves plus 4x plus c. Remember that 2/3 there in the middle, I'll highlight. This 2/3 came from the fact that you were dividing by 3 halves. That's the same as flipping and multiplying, right? When you divide by a fraction, it's the same thing as flipping the fraction and multiplying it. So this here would be our final answer. This is an antiderivative of the integrand up above. So just labeling one more time with the notation you might see in class, we would refer to this integrand function as little f of x. And then what you found down below here is big F of x. Big F of x is an antiderivative of the little f of x function. And if you weren't sure and wanted to check your answer, what you would do is take your big F, take the derivative of this function right here. So take the derivative of this function right here. You should get back that little f in the integrand. The best way to get better at these problems is just practice, so let's keep going. So in this next problem, I've given us a more complicated looking integrand, right? The integrand is the function we are looking to integrate. And we're just going to talk about how to deal with this. Now, a common mistake among students is they look at this integrand and what they want to do is they want to treat the numerator and denominator separately and just integrate them separately. That is not okay. That would be like neglecting your quotient rule. For example, if you were in differential calculus, you would need some sort of rule on how to take an integral written as a quotient, and right now you don't have that rule. You have a sum and difference rule, a power rule, and a constant rule. So what do we do then? How do we proceed to find big F, or find an antiderivative? And the answer first is algebraic simplification. So back to algebra before we begin our calculus. So we want to think of this problem as the antiderivative of 6x to the 3 halves divided by 2x minus, notice I am going to divide every term by 2x because that's what's being done in the original problem, just written in a different way. So I didn't change the problem at all. I just split it apart to make it easier for me to then continue on my algebraic simplification path before I actually integrate. So now that we're split apart, we need to simplify. So focus now algebraically on simplifying this 6x to the 3 halves divided by 2x. Remember some helpful exponent rules. So first thing I'm going to do is I'm going to divide the 6 by 2, results in 3. And then follow my laser pointer here. I need to clean up the x terms. And remember the rule here is you subtract exponents. So you would take 3 halves, subtract 1, and that'll give you your new exponent on x as you clean up. So all I did was I took 3 halves and I subtracted 1 to simplify. Same thing goes for the next term. Move over. So let's get a minus sign. Oh, I want to keep in the same color. So let's go get that minus sign. Good. Now, looking at, we've got 2 divided by 2 simplifies to 1. You can put the 1 if you want, but again, people don't tend to write 1s, so I'm going to take that off. And then subtract your exponents on your x to find that this just becomes x to the first power. But again, we don't write that 1 usually, so there it is. And then plus reduce what's going on over here, and this reduces just to 2. Awesome. So we have done some algebraic simplification. Now notice we're in a string where we can just apply the sum and difference rule, the constant multiple rule, as well as the power rule, right? We don't have any more nasty quotient. We clean things up, and now here comes the calculus. Let's integrate. So constant multiple rule tells me that this 3 just comes along for the ride. And power rule says add 1 to the power, divide by the new power. Move along to the next term. Remember, x has a power of 1 already, so you add 1 to the power, divide by the new power. Plus, now remember the 2, a constant being added or subtracted just on its own. Remember, that's thinking of like 2x to the 0. So what happens here is you just gain an x. When there's a constant on its own and you integrate, you just gain an x term. And then don't forget, we're finding a general antiderivative, so we have to keep including that plus c to indicate there could be a constant there as well. So this right here is definitely a final answer. This is an antiderivative of that original integrand. It's not cleaned up very nicely. I'll shrink this down and take a moment to clean it up, but I do want to point out this is a final answer, just written kind of sloppily. So let's just do a little bit of cleanup on that. So this becomes 3x to the 3 halves divided by 3 halves minus x squared over 2 plus 2x plus c. And of course, we could, if we wanted to, manipulate those fractions a little bit better and clean that up better as well. Just for the sake of time, I'm not going to. So both of these are totally valid answers for that antiderivative big F of x function you were looking for when the little f function was written in the integrand. Let's go down to 2.2. Let's just keep going. So 2.2 is actually very similar to 2.1. So this might be a great place to pause the video, try this problem yourself. Work ahead of me, try the problem yourself, get simplified, and then come back and rewatch and see if we match answers. If you don't feel confident to try that yet, then just work along with me. So we're evaluating an indefinite integral because there are no limits of integration. We would call this an indefinite integral. My first process is to do 2 things. 1, there's some wisdom in knowing to split what's in the integrand so I can clean it up algebraically. And 2, when I see a root going on there, I want to rewrite it as an exponent. So step one, the wisdom is to rewrite. So I'm going to take every term separately, divided by the denominator. And then I'm also going to rewrite the square root on my x as a 1/2 power. So I have got everything set up, ready for me to now simplify. So step one was the wisdom to rewrite. Step two here is this wisdom to then simplify. So all I'm doing right now is I'm going through each one of these terms and simplifying it down. Let's do the next term. Now remembering this last term, what you do with your exponents is you subtract exponents on your x. So 2 divided by 2 is 1 with the negative still there. And then what I need to do is I need to take 1/2 minus 1, which gives me x. Let's do it in blue, x to the negative 1/2. So just taking a moment to make sure that I didn't do anything silly. All I've done here is algebraic simplification. I'll just abbreviate algebraic simp. I just simplified. So notice I haven't really done any calculus yet. I haven't done any integrating. I rewrote the problem in step one. I simplified it algebraically in step two. And now I can begin my power rule and do the integration. Remember, once I do the integration, once I start my integration process, I don't write that integral sign anymore. Constant multiplier comes for the ride. Apply the power rule. Add 1 to the power, divide by the new power. The constant with no variable gains an x. And now we're also going to apply the power rule on a negative exponent. That's okay. You add 1 to the new exponent or the exponent, and you divide by the new exponent. This is what this looks like. And then don't forget, it's a general antiderivative, so we have a plus c. So this, again, this right here is a final answer. It's just a little bit of a mess. Let's clean it up. So I'm going to move it over on my screen here just to give me room. I'm going to clean this up. It's good practice to go through and occasionally algebraically clean things. Depending on your class or your teacher, you may be asked to algebraically clean antiderivatives, or they might tell you just leave them as is. So all I'm doing now is adding those numbers together. All I did was I cleaned up all those addition signs, and then I'm going to do one more step. I'm going to go through and reduce where I can. I have a 4 divided by 4 in the first term, so just clean that up. And then in the last term there, just remember dividing by 1/2 is the same as multiplying by its reciprocal, which is 2. So dividing by 1/2 is the same as multiplying by 2. That's why my answer converted. So you'll see this final answer here is a lot cleaner than the other answers, but I do want you to keep in mind, these are valid answers above. They're just not the cleanest form. I think what I have written there in the box now is kind of the cleanest way we could write that antiderivative, that big f of x function that we were looking for. All right, more practice, just more and more practice is how we get good at this. You start recognizing what forms you can take antiderivatives of, and then you start recognizing when you can't take an antiderivative and you need a different rule. Different rules are going to be coming to you in the course of your class you're taking. So let's look at example 3.1. Again, we're evaluating an indefinite integral. There's no limits of integration. Now look inside what's going on in our integrand. We have a product going on in there. Remember, You may not just look at each term of the product and integrate separately. That's not allowed. You're only allowed to integrate separately if there's a plus or minus between each term. We have multiplication going on between those two terms or two factors, so do not treat those separately. What do? Algebra simplification. We do algebra, I'll just write. It takes wisdom though, right? You have to look at this problem and say, oh, I can use the distributive property, or if you use the word FOIL, whatever word you use, and clean this up. So what I'm going to do is I'm going to distribute, right? Distributing through just looks like every term multiplies through. That's all I'm going to do. I'm going to go through that distribution multiplication process. So I get x to the fourth, I'm just going kind of slow, minus 2x cubed plus 3x minus 6. And then don't forget your dx is there. Awesome. So just kind of double checking here, I FOILed or I distributed that problem, those factors out. Double checking I didn't make a mistake. And now look, now I'm in a format of all pluses and minus signs. I can use the power rule to integrate each term separately. And of course, the constant multiple rule and the sum and difference rule is what tells us we're allowed to do this. So power rule in the first term, you add 1 to the exponent, divide by the new exponent. Keep going. The -2 multiplier comes with us. Take your x to the third, add 1, divide by the new exponent. Keep going. The 3 comes with us. Add 1. Remember, I had to put a 1 up there because there's an implied, I'll write it in the one above, there's an implied 1 exponent. So we had to raise to the 1 plus 1, divide by the new exponent, minus a constant gains an x, and then plus c. And this actually doesn't look too bad to clean up, so I'm going to do so. This becomes x to the 5th over 5 minus 2x to the 4th over 4. And we could do a little bit more reducing, which I'm going to do to show you. We have a 2 divided by a 4 hiding in there. So let's do this. I'm also going to rewrite it a different way, just something you want to get used to. You want to get used to looking at x to the 5 over 5 or a problem looking similar to that and realize that that can be rewritten as 1/5 x to the 5. So taking a moment here, you want to get good at recognizing those two circled terms are the same thing. I can write it as a quotient of the x to the 5 over 5, or I can pull out that 1/5 constant and put it in front, right? You want to think about there's a 1 up there multiplying by that x to the 5th. That's why I can rewrite it. So continuing, I'm going to reduce that 2/4 to 1/2 and pull it out in front. X squared, pardon me, minus 6x plus c. I had to bleed over to the other line as I ran out of room. But there would be the problem all kind of nicely written out. And notice I happened to change the format and pull my constants out front. That's something that's a good habit to get into doing, or just knowing you can go back and forth between the various forms. Let's keep cruising through and hit example 3.2. Now notice we have a couple of factors going on here. There's lots of multiplication, right? There's a factor with 3, an x minus 1 factor, and then a more complicated looking factor. Now, one of the rules we talked about was that constant multiple rule. And I'm going to show you if we rewrite this using that constant multiple rule, some people pull that 3. So because that 3 right there is multiplying every single term, some people will just pull that 3 out in front. So what this will look like is 3, then you write your integral sign, x minus 1, 2x plus, now instead of x to the square root of x, I'm going to rewrite it as x to the 1/2. So here is one way this problem can be rewritten. You also could leave the 3 multiplier inside. This is a matter of personal preference, whether you pull constants out in front or whether you leave them in the problem and just deal with them as you integrate. In this example, just to show something different, I am going to leave the 3 outside for this entire problem, just to show you what that would look like. So now, leaving the 3 outside the integral sign, I need to go through my distribution or foiling process to clean up this integrand, right? I cannot treat each term separately because they are being multiplied. I must do something, and that means let's clean it up. So multiplying it out, I get 2x squared plus x to the 3/2. I'm going to pause real quick and tell you where this x to the 3/2 term came from. So the first thing I did was I multiplied x by 2x to give me 2x squared. Then I multiplied x by x to the 1/2. Remember, you add your exponents. So showing that one more time, if I take x to the 1 and multiply it by x to the 1/2, I added my exponents and got x to the 3/2. Now, continuing along, I'm going to take -1 times -2x, or excuse me, times 2x, which becomes -2x. And then I'm going to take -1 times the last term there. So -x to the 1/2 dx. Notice now I'm in my nice long string, and now I can apply the power rule to every term. And as you do that, be careful. So this is going to equal. Notice I have a 3 out in front. I took that 3 out in front. So it's going to be 3 times, because I'm going to integrate now. So I get rid of the antiderivative sign, that integration sign, and I'm just going to take the antiderivative of each piece separately. Constant multiplier rule comes along for the ride. Add 1 to the power, divide by the new power, plus x to the 3/2 plus 1, divide by the new power, plus 1, minus. Okay, I'm going to move my text over just to give me more room. I'm running out of space. So where did I leave off? I left off on the third term. The -2 comes with me. Add 1, divide by the new power, minus add 1, divide by the new power. That is a lot going on there. And don't forget your plus c. Normally we'd close up the parentheses after the function, all the x's before the plus c. And remember, this 3 is essentially being multiplied to every single term because we pulled it out of the integration sign to begin with. So that's the appropriate way to show that. And there's a variety of ways you could clean this up. I'll just do a one-step cleanup, but this could obviously be cleaned up in probably multiple different formats. Right, we have a fraction inside of a fraction going on the second term. You could clean that up a little differently. So there's a lot of text going on here, but I'll just box this. This could be one form of your final answer. But again, there's a lot of messy stuff here. So if your teacher focuses on cleaning up, you might need to go through not divide by a fraction, multiply by the reciprocals. And then you might also need to go through and reduce your 2's, reduce your fractions. Another thing you could do in the cleanup process is you could also distribute that 3 through to every single term. Let's keep going. Now we just have a few more practice problems and we'll call it good. So this would be a great time as well. Pause the video, work through, there's 3 more practice problems on this page, and then come back, check your answers against mine. I am going to throw in one more piece of information after we do this practice problems about the power rule, so make sure you watch that. That's going to be important. But let me just work through these practice problems first, and then I'll throw in one more nugget of information that you'll want. So looking at this problem, the integrand, what I do is I check out the structure. Do I need to rewrite any roots? Do I need to do any algebraic simplification? Does anything need to be cleaned up? To me, nope, it looks just like a nice long string. So I'm going to start taking antiderivatives. Apply the power rule. Remember the 5 constant gains in x, and then we have a plus c for our generalized antiderivative. That's just working through each term. I know I went through that a little fast. You will eventually get this fast too when you get enough practice in. Just cleaning up. So here would be one way to write your final answer. I will take the time to show you what this might look like a little bit cleaned up. So let me just make that a little smaller. Let's squeeze in. A different form of your answer could look like, I prefer to pull constants out in front. So if I were doing these problems and this were my homework, my preferred form of the answer would be written on the right side there. But those are equal statements. Remember, dividing by 5/2 is the same as multiplying by 2/5, and then I like to pull it out in front of the x term. All right, problem 4.2. Oh, this looks a little more cumbersome. I definitely check out my integrand. Do I need to do any rewriting or dividing? And the answer to me here is yes. I do need to do some rewriting and algebra. So start on my path. This is all just housekeeping and cleanup work. Every term is being divided by 5x, and rewrite your root as a power. So just double checking what I've done here. I've split across the denominator. I've rewritten my root as a power. I'm double checking no mistakes have been made. Now I am going to simplify this, just reduce each term. So, right, I have not integrated yet. I am just doing my housekeeping. That first term, 10 divided by 5 is 2. Simplify your x terms. Don't forget, right, what I'm doing to simplify my x terms is I subtract the exponents. Minus, let's keep going. Oh, there's a 1. 5 divided by 5 is 1. You could write the 1 or not. Subtract your exponents. That becomes negative 1/2. Right, I'm subtracting the exponents on those x's. And then the last term reduces to 2/5. All right, so now I am primed and set up to take my antiderivative. Applying the power rule to each term. Add 1, divide by the new power. So now I'm not going to show that plus 1 anymore. You're just going to take 2 plus 1 becomes 3. Divide by the new power. Negative 1/2 plus 1 becomes positive 1/2. Divide by the new power. And then your 2/5 just gains an x plus c. And there we go. We have a final answer here. We're going to call this good. Again, that middle term has a fraction inside of a fraction. You could clean that up as well. But this would be considered to be a final answer. And then one more practice problem. We did one like this similar. Remember the practice problem I did before, just recently? I pulled the constant multiplier out. So in this problem, I'm not going to pull the constant multiplier out, just so you can see both ways it's done. So I'm going to leave the constant multiplier in, and I'm just going to do some algebra here. So leave my 2 alone for a minute. What I'm going to do is I'm going to FOIL out, or distribute those two more complicated factors there. So notice I've left the 2 alone, and now I'm going to multiply out all of these terms up above. So 3x squared so I have multiplied all of those terms out. I'm just doing a quick double check, make sure I didn't do any silly mistakes. Now again, if you like to pull the 2 out, you absolutely could. However, you can also incorporate the 2 into your function, which I am going to do now as well. I'm going to multiply everything by 2. I can't forget about the 2, so I need to do something with it. So this 2 either needs to come out of the integrand or needs to be incorporated into the integrand, which I'm going to do. I'm going to multiply every term by 2. So there it is. Double checking and then moving just to make more space for our final answer. So again, up until this step, I have not done any calculus yet. I've just done my housekeeping to get me prepared now to take an antiderivative. Now you'll also note there are like terms in the middle. You could combine those, or you could just integrate each term and combine at the end. Let's say we did want to combine those like terms. This would become 6x squared minus 2x minus 8 dx. So these like terms could have been combined in this step or in the step above. You will wind up with the following integrand that I'm at. Now we are primed and ready to take an antiderivative. So all that prep work, now we start our antiderivative process. This is where we lose the integration sign. We apply our power rule, add 1 to the power, divide by the new power, add 1 to the power, divide by the new power, and then that constant 8 gains an x. And then since this is a general antiderivative, we have to keep in mind there could have been a plus c. Let's clean this answer up. 6 divided by 3 is 2. So there it is. There's the final clean answer at the end of the day. And remember, if you wanted to check your answer, one thing you could do is take your final answer, take the derivative of this final answer. So take the derivative of that final answer, and you should get your integrand function as the answer. So I told you I was going to add one more quick tidbit and note. So this is an important note about the power rule. Power rule does not apply to integrating x to the negative 1. This is very, very important. So if you are asked to integrate x to the negative 1 dx, I'm going to put here, do not use the power rule. So big, sad face. Do not apply the power rule. And I want to remind you as to why. The negative 1 is an instance where we can't use the power rule. And this is going to require you digging deep back to your differential calculus class. So recall, we'll say. I'm going to just write this a little bit differently. So if x to the negative 1 is my derivative, that's the same as 1 over x if I rewrite it. Think back to your differential calculus class. What function has its derivative of 1 over x? So this is a rule you did memorize, or probably were supposed to memorize at some differential calculus. So in some differential calculus course, what function's derivative is 1 over x? And the answer to that, if you recall, was your natural log function. The natural log of x has a derivative of 1 over x or x to the negative 1. Those say the same thing. So this is a rule you have to recall. Therefore, this is an integration rule your teacher will probably discuss, but usually introduces during the power rule section. Therefore, the antiderivative of x to the negative 1 dx is equal to the natural log of the absolute values of x plus c. Now, notice I incorporated absolute values on x. This goes back to understanding your natural log function from algebra and remembering that it has domain restrictions. You have to only plug in positive numbers as input to a natural log function. So that's why the absolute values appear when you take an antiderivative. So the power rule works for all powers on x except for negative 1. This is the one exception here. So just to show you one more example with this, if you were being asked to integrate 8x to the negative 1 dx, this would just become, the 8 comes along for the ride, and then you'd have to remember, do not power rule if the power is negative 1. Apply the concept that that is the natural log of x plus c. That wraps up just the basics of our integration techniques. Check back, we'll end up talking about more techniques as functions get more complicated. What happens when you have functions inside of functions you want to integrate, or functions multiplying other functions that you can't clean up algebraically? What happens when you involve an e function or a sine function? So many more things to come on what we're going to learn to find the antiderivatives of.